Hello students, welcome to TSS Tutorial Center, where we make complicated topics very simple to understand. So if you are under natural in the applied sciences and you want to become good, you want to become better, you want to start thinking outside the box, then do subscribe to this channel because we break down complicated topics to something which you're going to understand in just a short period of time. Fima Zwibo! Zwibo dude. In this tutorial, we'll talk about collision theory, and I assure you it's very simple to understand. You see how I'm going to break it down. Okay, so we'll start with collision theory of chemical kinetics because it is the continuation of chemical kinetics. Now, it is worth mentioning that the chemical kinetics theory proposes that all gases collide for them to react. There can't be a reaction without the molecules colliding. So there's supposed to be collision. Now we'll talk about it. It's not every collision which is going to lead to a chemical reaction. There can be a touch, but nothing is going to change. There's not going to be any reaction. I'm sure you're going to understand. Just stay tuned with me and I'm sure I'm going to break it down to you. Okay, so the collision theory explains that the rate of reaction is directly proportional to the number of collisions per second. Okay, so when they collide, the more they collide, that's the rate of reaction. That's how it's going to flow. Now, we're saying there's some condition. It's not every collision which is going to lead to a chemical reaction. Also, now let's talk about the conditions. What are the conditions for a reaction to occur? Okay, so we said you're supposed to think of collision theory somehow like a fight. And people, they are fighting. Can you fight? You don't have energy. Can you fight? You don't even have energy to move. Even to throw a punch, you don't have that energy. Then no reaction is going to be there. So that energy that I'm talking about, I want you to think of it in this way. You'll be enjoying it. That energy that I'm talking about is known as the activation energy. So the colliding molecules supposed to have the total kinetic energy, which is greater or equal to the activation energy, and they should be properly oriented or arranged, because you can't fight with someone. You are facing your back, you're giving each other the backside. No, it's supposed to be facing properly. So even the way you are supposed to arrange yourselves is very important for a reaction to occur. Are you getting my point? Now let's talk about the energy. We're saying the colliding molecules supposed to have the total kinetic energy greater or equal to the activation energy. Now, what is this activation energy? That is the energy that I'm talking about. The energy you're supposed to have for you to start a fight. This is the minimum energy required to break the bond and start a chemical reaction. The minimum energy required to break the bond and start a chemical reaction. That is the definition. It's actually very simple. Now, think about it. When the colliding molecules, suppose we have two molecules, this one and this one, they are moving. They're supposed to collide for them to react. When they are moving, what energy are they possessing? They're definitely possessing what is known as kinetic energy because they are in motion. Now, the faster they move, don't you think that is the faster the kinetic energy is? Exactly. So the faster they move, the faster the kinetic energy, or the greater the kinetic energy they are going to possess. Now, when they collide, what happens is this. When they collide, boom, the bab could bantu bamonaka bar promoter. That kinetic energy will be converted to vibrational energy. Vibrational energy will cause the particles inside the molecules to vibrate. Now that vibration is going to break the bonds, so they'll start breaking, and finally they will react and form one thing. It will become one thing. You've seen Now ask yourself, we are saying the greater they move, the faster they move, then the higher the kinetic energy they are going to have. Now what if they are moving, yes, but the kinetic energy is low, like they are moving very slow. When they boom collide, is there going to be a reaction when the kinetic energy is lower than the activation energy? No, there's not going to be a reaction, because you're saying you don't have energy to fight. You can touch the person, but you can't fight. This is exactly what we're talking about. Okay, so there we go. I want us to break it down to you in a way that you're not going to forget. So that's what we're saying. We were saying when the kinetic energy is low, it's too low, the vibrational energy produced is not going to be sufficient to break the bonds and to start a chemical reaction, which means no chemical reaction is going to occur. So when we say, or you hear someone saying that every collision leads to a chemical reaction, fire in the name of Jesus, it doesn't happen that way, unless if the kinetic energy is equal to or greater than the activation energy. And we've also talked about orientation. Orientation is very much important. Orientation, how they have been arranged for them to react. So there's just two conditions. The first one, the activation energy. The second one, just talking about orientation. Okay, let's move on to something else. Now let's say we have two molecules, like we gave an example. They collide and they have sufficient energy to break the bonds. Now they start breaking, but the new substance has not yet formed, but they are breaking. This guy has been given a name. When the colliding molecules are breaking, but the product is not yet made, that complex or that state is known as the activated complex. It is also known as the transition state. It is known as the activated complex. Sometimes people say activation complex or transition state. Now in definition, what did we say? We said when the molecules collide but the product is not yet made, then that state is known as what? Activated state. This is what we're saying. And the activated state is unstable complex. We're going to talk about this, and it actually have large amount of energy compared to the product, compared to the reactant. It's the one at the highest point. Okay, so there are some graphs we'll talk about, and they are very simple. And I remember in the test we were asked, even in the exam. So let's go. Okay, to the diagrams. The first one, they are known as profile diagrams, NH profile diagrams. The first one talks about this reaction known as endothermic reaction. Do you still remember this reaction? I bet you do. Okay, so this is the reaction where energy is absorbed from the surrounding. Not so. Is absorbed from the surrounding. Then there is exothermic, where energy is what? Is given out. Now, let's go dive into it. So, when it comes to endothermic, the reactants are considered to be stable than the products, or the reactants, they have lower energy compared to the products, which means the products will have greater energy. This is what the statement here is saying. The reactants are going to be more stable. They are going to be rich. I used to say they are richer. And when the energy of product is greater than that of the reactants. Now you're supposed to know the diagram. How is it going to be? So the profile diagram is going to have the reactant, the activated complex, and the products. in the energy cell. Okay, so yeah, like we said, heat is absorbed from the surrounding. Now let's talk about how the diagram is going to be. Okay. Okay, so the y-axis is going to be the energy. Then how it's going to be is this. The reactants are going to be this side, then the products are going to be this side. So as the reactants were reacting, when they reached here, it means the bonds have started to be broken already. Now, this guy, the product is not yet made. And we talked about this part which is here. When they are breaking, but the product is not yet made, we called it the what? The transition state, which is also known as activated complex. Okay, so on top here, this is known as the what? The activated state. And from here to there, this energy used is known as the activation energy. Very simple. So make sure you know how to draw these simple diagrams because they carry a lot of marks. Let's move on to the next reaction known as exothermic reaction. Very simple as well. Okay, so we know that heat energy is given out from the surrounding. Now, in this one, you have seen here, it's just going to be the opposite. We're saying that the reactants are more stable. When it kind of approaches this guy, then it is stable. But if it is away from this guy, it's not stable from this line. Okay, so just going to be the opposite, and we know what opposite means, which means the products are going to be what? Stable. They are going to be rich, but the reactants they are going to be what? Unstable, and they will have high energy compared to the products. Okay, so let me show you how to draw the diagram for this one. I've talked about this. I've talked about this as well. Okay, so the bar bantu bamanaka bar promoter. How is it going to be? There we go. We know that there's going to be reactants in products. Now it's going to be the opposite. So it will be something like this. And we know that this is going to be the activation energy. So it is always from this line of the reactants to where the activation complex is. And we know that at the top there, that is where the activated complex is going to be. Okay, so we move on to I love this word. Okay, so this one is known as Arrhenius equation. Actually, I used to enjoy whenever the sir will say Arrhenius equation. Anyway, let's talk about the Arrhenius equation. It's actually very simple. Okay, so what to know about this guy? I don't want you to start confusing yourself about it. Make sure you just understand the formula and the things that I'll talk about. Okay, so this is the formula. If you can't see it, or if you have eye problems, it is more like this. Though it is not this one you're going to be using, we're going to break it down in a way that gonna be very simple for you to use it. Hey, something like this. There. Okay. Now, you can know the terms, but it's not really necessary at this point. There is somewhere I want us to go, but it's going to be very important, and I'll tell you that this actually come in the exam, and you'll be asked such a question about this and that. Okay, so let's go to it. The formula is like this. When we simplify it, it's going to be something like this. Now from this formula, there is something we can derive. Okay, so you should know how to find the activation energy. Okay, so let's do some math. We're not going to take a lot of time on that. I'll show you how to deal with this guy. Okay, so we have an equation which is K. Let me start from here. K is equal to A, an exponent, raised to the power. This is the power activation energy divided by RT. Okay, so what you do is you're going to introduce ln on both sides. Even this side you introduce. Okay, so AE means activation energy. Now look, when you're talking about rules of logarithms, actually there is this one. When they are multiplying, you add, you expand by adding. So we're going to expand this guy. By adding. Even why some people say it's nice, very complicated. Anyway, according again to the rules of logarithms, we can drop the power. Not so. So we're going to drop the power. Look at this, dropping the power. Let me drop it from this side. It will be negative AE over RT, then ln. This is also known as log of E, K, ln A, ln K, and this is going to be, okay, pam. Okay, so this guy is just equal to 1. This is the formula we have. So this formula is very important. Why? Because from this formula you can tell that you're going to have a slope and a straight line. They're going to ask you what they're going to ask you ln k versus what? For it to form a straight line, it's going to be against what? Okay, so let me show you. So this formula is in form of y is equal to mx plus c, and now this is going to be the value of y. Then the gradient is actually going to be given by activation energy divided by what? The gas constant plus ln A. Okay, so when we draw a line ln K versus 1 over T, then we're going to have a straight line. Okay, so this is very important. In this, again, it's worth mentioning that negative activation energy divided by R, that is the slope. Okay, so this is the formula which is very important, but again, this one just tells us the slope, the straight line. There is another one. Let me show you. When we combine two of these equations, we're going to have this equation. Very simple, but actually a lot of people don't know how to apply it, but it's actually very simple. Okay, so this is what I was talking about. Then the graph is going to be ln K versus 1 over T. And it's going to be a straight line. Since the slope is negative, so it's going to be going down like this. Then again, ln A is the y-intercept. And take note, when you have your values of ln K and 1 over T, you can plot the graph and use the points to find the activation energy. So it's very simple. Now, you know how to find the slope from grade 12. We were saying the slope is actually given by what? y2 minus y1 over x2 minus x1. Same situation here. The value of x is 1 over t. So it can be ln k2 minus ln k1. Now here is supposed to be 2. Then there is supposed to be 1. Okay. So that's the way it's supposed to be. You can find the slope. When you find this, then you equate it to the negative activation energy divided by R. Then you can find the activation energy, because R, we already know that it is just a gas constant and ln k actually it has no units, so don't even bother, it has no units. But then what we would do now, the Arrhenius equation, the main one, the equation that you're supposed to know, you combine two of these equations. So for two different temperatures, this is the formula you're going to be using. This is the formula you're going to be using. It's very much important. When you simplify it further, you're going to have something like examples on how you can use the Arrhenius equation. A lot of people, you are able to memorize it, you know the way it is, but you don't know how to use it. That is how to make the subject to the formula of the thing you're looking for, and how to punch everything on a calculator. So I'll show you how to do it. According to the question, the rate constant of first order of reaction is 3.46 times 10 raised to the power negative 2 at a temperature of 298 Kelvin. What is the rate constant at 350 Kelvin if the activation energy is 50.2 kilojoules per mole? Okay, so make sure the temperatures, they are in what? They're in kelvins. Okay, so the formula is ln k2 divided by k1. Then we equate this to be equal to activation energy divided by the gas constant. Then this side, T2, not T1, T2 minus T1, then over T1 times T2. The formula is very simple. What you should know is the temperature supposed to be in Kelvin, and the gas constant, the one that you use, it is actually not 0.8, it's 8.314. In this case, we'll be using this guy. Let's go about the question. The question is asking us to find the rate constant. We're going to code that rate constant as K2, which means for the K1, we know it is 3.46 times 10, then raised to the power negative 2. So since K1 is equal to that, even T1 is going to be 298 Kelvin. So what I don't have is K2, but I know that my T2 is 350. Okay, so I'm going to make this guy the subject without substituting anything. I'm just going to make it the subject, and I'll substitute at the end. Okay, so look at this. ln is same as log E. So what we'll do is, if this is same as log E, then I can also write here as log E. This E, I'm trying to make this log disappear. So this E will go this side, and it's going to make everything which is this side become the power. That's where the complication comes in, but it's actually simple. But that's where a lot of people now sees, now, how can you have such a bigger power? How am I going to operate? It's just very simple, you know. So this is going this side, making everything on the right hand side becoming the what? The power. So this side I'm going to remain with K2 divided by K1. So when it goes that side, the E, boom, everything becomes the power. You are just going to denote it like this. Then you put everything in brackets. So we have T2 minus T1. Then here we know that it's T1 minus times T2. You see, it's very simple. Making this guy the subject, you cross multiply. So this guy will just go this side. So you're going to have K2 being equal to K1, then the exponent of this entire thing. T2 minus T1 over T1 times T2. Okay, it's actually very simple. Then I'll substitute everything. Okay, so K1 is this number that I have here. So I'll substitute the same number. 4, 6 times 10 raised to the power negative 2. What else? I'm going to substitute the activation energy. So activation energy is in kilojoules. So I'm going to multiply by 1000. 6.2 times 10 raised to the power 3 because of the kilo. Because of this kilo. What else? I'm going to divide by the rate constant. 3.8.314. Then in the brackets. Okay, so we're starting with T2, which is T2 and 350 minus T1, which is 298, then divided by the product of these two guys. Let's punch this on your calculator. I'll show you how to do it soon. Examples on how you can use the Arrhenius equation. A lot of people, you are able to memorize it, you know the way it is, but you don't know how to use it. That is how to make the subject to the formula of the thing you're looking for and how to punch everything on a calculator. So I'll show you how to do it. According to the question, the rate constant of first order of reaction is 3.46 times 10 raised to the power negative 2 at a temperature of 298 Kelvin. What is the rate constant at 350 Kelvin if the activation energy is 50.2 kilojoules per mole? Okay, so make sure the temperatures, they are in what? They're in kelvins. Okay, so the formula is ln K2 divided by K1. Then we equate this to be equal to activation energy divided by the gas constant. Then this side, T2, not T1, T2 minus T1. Then over T1 times T2. The formula is very simple. What you should know is the temperature supposed to be in Kelvin, and the gas constant, the one that you use, it is actually not 0.8, it's 8.314. In this case, we'll be using this guy. Let's go about the question. The question is asking us to find the rate constant. We're going to call that rate constant as K2, which means for the K1, we know it is 3.46 times 10 then raised to the power what? -2. So since K1 is equal to that, even T1 is going to be 98 to 98 Kelvin. So what I don't have is K2, but I know that my T2 is 350. Okay, so I'm going to make this guy the subject without substituting anything. I'm just going to make it the subject, then I'll substitute at the end. Okay, so look at this. ln is same as log E. So what we'll do is, if this is same as log E, then I can also write here as log E. This E, I'm trying to make this log disappear. So this E will go this side and it's going to make everything which is this side become the power. That's where the complication comes in, but it's actually simple. But that's where a lot of people now says, nah, how can you have such a bigger power? How am I going to operate? It's just very simple, you know. So this is going this side, making everything on the right hand side becoming the what? The power. So this side I'm going to remain with K2 divided by K1. So when it goes that side, the E, boom, everything becomes the power. You are just going to denote it like this. Then you put everything in brackets. So we have T2 minus T1. Then here we know that it's T1 minus times T2. Now you see it's very simple. Making this guy the subject, you cross multiply. So this guy will just go this side. So you're going to have K2 being equal to K1, then the exponent of this entire thing. T2 minus T1 over T1 times T2. Okay, it's actually very simple. Then I'll substitute everything. Okay, so K1 is this number that I have here. So I'll substitute the same number. 4, 6 times 10 raised to the power -2. What else? I'm going to substitute the activation energy. So activation energy is in kilojoules. So I'm going to multiply by 1000. 6.2 times 10 raised to the power 3 because of the kilo. Because of this kilo. What else? I'm going to divide by the rate constant. 3.8.314. Then in the brackets. Okay, so we're starting with T2, which is T2 and 350 minus T1, which is 298, then divided by the product of these two guys. Let's punch this on your calculator. I'll show you how to do it soon. Okay, so this is what you should get. I know you are thinking, how did I do this? Okay, so let me show you how to punch this on a calculator. Remember what we had? We had something like K2 being equal to 3.46 times 10 raised to the power -2. And there was something like this, 50.2 times 10 raised to the power 3, and the gas constant 3.8.314. Then inside the brackets there was 350 minus 298 divided by 350 times 298. Okay, so if you just know how to punch this on a calculator, this formula, you're going to be enjoying it. Okay, so what you do is this. Get the calculator wherever you are. I will be showing you the steps. You're going to subtract 350 minus 298. The answer is going to give you, don't write it down, just punch again. Punch the answer you're going to get divided by what you have as the numerator. Divide by this. So we have dealt with this first bracket. The answer that you have gotten, don't write it down, multiply directly by 50.2 times 10 raised to the power 3. What you're going to get again, divide by 3.8.314. And there was exponent here. There was exponent here, don't forget. Okay, so this exponential just raised to this power. Okay, so what I'm saying is you subtract 350 minus 298. The answer you're going to get, divide by 350 multiplied by 298. The answer you're going to get here, you multiply by 50.2 times 10 raised to the power 3. The answer again you're going to get, divide by 8.314. You're going to get 3.0103 when you punch him. Then again, go on your calculator, find where the exponent is. Most of the calculators you're going to press shift, then you place on the exponent. Okay, so do so, then just say equals. After you press the exponent, it comes on your calculator. Just press equals, then there will be answers. It will be something like this. The answer that you got equals, then it's going to give you a certain number. That number multiplied by this one, then you're going to get this. Okay, so when you just know how to use the formula, then everything will just going to be cool for you. That's how we use the Arrhenius equation. And you can try to check the paper that we wrote. This question is there in the past papers. So the bad for the Babantu Bamonaka Bapromoter. Thank you for watching.